Let's continue with our lecture on mathematical methods. Today we are looking at some of the application of analytic function, especially from the physics point of view. We are developing some formalism so that we can start applying this concept to the physics problem. So this is application of analytic function for the course PH3103 at IISER Calcutta. So let's quickly go over the summary of complex function. So we have seen that a complex function is analytic at a point z0 if f of z is differentiable at z0 and at every point in some neighborhood around z0. A function is analytic at every point in z plane, then we call such function an entire function. So if f of z is equal to u of xy plus I into v of xy is differentiable at point z is equal to x plus iy, then the function u of xy and v of xy would satisfy Cauchy-Riemann condition if the function f of z is differentiable. The Cauchy-Riemann condition is given as a partial derivative of u with respect to x must be equal to partial derivative of v with respect to y, and partial derivative of u with respect to y must be equal to minus partial derivative of v with respect to x. A real valued function of two variable phi of x, y is said to be harmonic if it satisfies the Laplace condition. Obviously, the function need to have well-defined first and second order derivatives in the domain D. So, for the harmonic function, we have a del square phi by del x square plus del square phi by del y square should be equal to 0. So let's continue with some of the properties of analytic function in connection with the harmonic function. A complex function f of z is equal to u plus I v is analytic in domain D, then the function u of xy and v of xy are harmonic in D. So this is the main connection where we have two u of xy and v of xy of two variables satisfies the Laplace equation. Then we have a complex function which is defined as a u of xy plus I into v of xy is analytic in the domain, or other way around. So this is an important property, and let's have a look at the proof how we can do it if we have a property of a differentiability or analytic. The function is analytic, then it should satisfy Cauchy-Riemann condition, that is du by dx must be equal to dv by dy, and we must also have du by dy must be equal to minus dv by dx. Let's differentiate the first equation with respect to x. Then we get del square u by del x square must be equal to del square v by del x del y. On the other side, we differentiate the equation with respect to y on both sides. Then we get del square u by del y square must be equal to minus del square v by del y del x. Now we add these two sides, and then we get del square u by del x square plus del square u by del y square is equal to 0. That means the function u is harmonic given the condition that the f of z is analytic. Let's also show that the v is also analytic. It proceeds in the same fashion. You take the Cauchy-Riemann condition, differentiate with respect to y on the both side for the first equation, differentiate x on the both side, then you subtract from one another, then you get del square v by del x square plus del square v by del y square is equal to 0. So we have seen that the both function u and v satisfy the Laplace equation, hence they are harmonic. So it is extremely useful property if you are looking for more and more solution to Laplace equation. All you got to do is a complex function which is analytic in the given domain or complex plane itself. So let's look at an example which we have already seen, that f of z is equal to z square, that in terms of x and y as x square minus y square plus I 2x y. Now we have a u is equal to x square minus y square and v is equal to 2x y. So we differentiate u with respect to x, we get 2x, which is same as differentiating v with respect to y. So it satisfies the first Cauchy-Riemann condition. Let's take a differential of u with respect to y. Now we get minus 2y. It is the same as multiplying minus 1 into differentiating v with respect to x. So we get Cauchy-Riemann condition satisfied for this both equation, and we see that this is an analytic function. We have already shown it from first principle. Also it is a polynomial, so it should be analytic in the complex plane. Let's look at the harmonic property. Del square u by del x square is equal to 2 and del square u by del y square is minus 2. So sum of them is 0, so u is a harmonic. Same way, let's look at the v. Del square v by del x square is equal to 0 and del square v by del y square is equal to 0. So this trivially satisfies the harmonic condition. Nevertheless, it is an harmonic condition. So this function is harmonic. So both we have u and v is a harmonic for the function which is analytic. Let's define what is called the harmonic conjugate function. We have seen the function f of z is equal to, this should be u of xy plus I times v of xy is analytic in some domain. Then both real and imaginary part u of xy and v of xy are necessarily harmonic. So this is a property of analytic function. Both their real part and imaginary part are a harmonic function. Now suppose we have given only a one function u of xy, and in a given domain it is a harmonic. If it is possible to find another harmonic function v of xy such that both u and v satisfies the Cauchy-Riemann condition throughout the domain D, then the function v is called the harmonic conjugate of u. By combining these two functions, f of z is equal to u of xy plus I times v of xy, we obtain a function which is analytic in the domain. So it's an extremely useful set of condition where which you have been given a one function which is harmonic. You find out another function which is harmonic as well as satisfying the Cauchy-Riemann condition, then you would call them harmonic conjugate of each other. By combining them, you construct a complex function which is analytic in the domain. Let's look at some examples. The first is to verify that the function u of xy is equal to x cube minus 3xy square minus 5y is a harmonic in the entire complex plane. So that is, we have to show that it satisfies the Laplace equation in two dimensions. So we take del u by del x, that is 3x square minus 3y square, and del u by del y is equal to minus 6xy minus 5. We differentiate again. Del square u by del x square is 6x, and del square, be a square here, del square u by del square y is equal to minus 6x. Naturally, it satisfies the Laplace equation and hence it is harmonic. Let's go ahead and find the harmonic conjugate function v of xy for a given function u of xy. For that, we need to satisfy Cauchy-Riemann condition and obtain the function y. Du by dx is equal to 3x square minus 3y square. And if you want to find out v such that it is satisfying the Cauchy-Riemann condition, then we should have this is equal to dv by dy. From this, we can integrate to obtain v of xy as a 3x square y minus y cube plus h of x. Because it's a partial differential equation, there is an uncertainty about the solution as a function of h of x, which we can pin down based on the second of the Cauchy-Riemann condition, that is dv by dx, that is 6xy plus x prime x must be equal to minus du by dx, which is 6xy plus 5. So from this we figure out that these terms cancel out, and then we have 5 is equal to h prime. So integrate this and then we get h of x is equal to 5x plus c, where c is a constant. Now we have found that v of xy is equal to 3x square y minus y cube plus 5x plus c. So these two are the functions which are harmonic conjugate of each other. So we can see that it satisfies the Cauchy-Riemann condition, both satisfies the Laplace equation. Now the next question comes about is the uniqueness. Of course, this harmonic conjugate is unique up to a constant of adding up the constant that we have seen here. Now let's say that let's flip around the role of u and v. Instead of just simply calling the function as a u, we can call it as a v as well and proceed to solve in the same manner. And then you would see that we would so let's say that you have a function f of z is equal to u x of y plus I v of x y, which is analytic in some domain. Then the real and imaginary part of f of z can be used to define two families of curves in D with the equation u of xy is equal to constant, v of xy is equal to constant. Constants are named C1 and C2 here for the convenience. And these curves are called the level curves of u and v. The concept essentially comes from the equipotential lines. We already know that it's when the function is analytic in a domain, real and imaginary part of the functions are harmonic or satisfy Laplace equation, which is a kind of a potential from the physics perspective, and these curves are like equipotential surfaces. And what it says is that these two curves are orthogonal families, roughly saying that every curve are orthogonal to each other. For a given point, we have a curve passing through that u and v, and their tangent is orthogonal to each other. So you have a curve u of xy is equal to u0 or c1, and you have a tangent L1. You have a other curve which is v of xy is equal to constant, and then that has a tangent L2. And what this says is that these two tangents are orthogonal to each other, and this happens at every point inside your domain. Let's see how to show this based on the or using the Cauchy-Riemann condition. Let's start with the u of xy is equal to constant and v of xy is equal to constant. Let t be the parameter along this curve, so we can independently parameterize this with the t, that what we do as a motion of particle, or we can simply use either x or y as a parameter, but I am using t as a parameter. Then the tangent vector L is along u of x t, y of t is equal to constant, is given by dx by dt, dy by dt. In addition to that, it satisfies the condition that du by dx, dx by dt plus du by dy, dy by dt is equal to 0. This is essentially saying that it is du is equal to 0 or u of xy is equal to constant c1, that is a curve which is being represented by this equation. So this is nothing but saying that you have a family of curve u of xy is equal to constant. Now we can substitute this back in our tangent vector and write this cumbersome equation, but actually it is fairly simple. You can see that, and dy by dt factors out. Same thing you can do for the tangent vector L2, which is tangent to the curve v of xt, y of t is equal to constant. Again we have a tangent vector dv by dt that is equal to dx by dt, dy by dt, and since v of x and t is equal to constant, we also have d of v is equal to 0, explicitly dv by dx, dx by dt plus dv by dy, dy by dt is equal to 0. That is to say that curve is described by v of xy is equal to constant. Now we can substitute back into this expression back into the tangent vector, and we obtain cumbersome looking expression for the tangent vector factoring out dy by dt. Now we take the dot product between the L1 and L2, then we see that these two cumbersome expressions are getting multiplied with respect to each other, then plus 1 into dy by dt. It's a time to use a Cauchy-Riemann condition into this equation and try to simplify this further. We have a du by dy cancelling out with the dv by dx, and du by dx is cancelling out with the dv by dy from the Cauchy-Riemann condition. This becomes a minus 1, and together we get the expression 0, which is telling that the vector L1 and L2 are orthogonal to each other. Since we have not taken any specific point, it is true everywhere in the domain wherever the Cauchy-Riemann condition is satisfied, that is the function u and v are analytic or harmonic conjugate of each other. So this is also a very useful result to understand. So let's look at the example where we have a curve f of z is equal to z square x square plus y square minus 2i xy. So we have u as a x square minus y square and v as a 2x into y. So we are looking at the functions which is x square minus y square is equal to c1 and 2xy is equal to c. So you can see the curves. These are the curve. The first one curves the parabolas across these, which are given by the u of xy is equal to constant. The second ones, which are going like these, are the orange curves, which are the curves corresponding to v of xy is equal to constant. Now we see that we can look at it, and whenever these two curves cross each other, they are actually orthogonal to each other. Either you can look at their tangent vector or their normal vector. You can see that they are becoming orthogonal. For example, let's take a point here. So this is the tangent vector to the orange curve, and this is the tangent vector to this curve. If you draw properly, you can see that they are orthogonal to each other. Same thing is valid at every point. Instead of drawing, you can actually calculate the tangent vector at each point and show that orthogonal. It is not necessary. We have already proved the theorem by which it is valid because we see that these two functions are harmonic conjugate of each other. Let's quickly define some of the geometric concepts to make the connection proper. The gradient of a function of two variable f of xy is given as a gradient of f is equal to df by dx into I cap plus df by dy into j cap. I cap is equal to unit vector along x-axis, that is 1, 0, and j cap is a unit vector along y-axis, that is 0, 1. So the gradient is a vector field generated by differentiating a function of 2 variable or n variable. We are confining to 2 variable because we are connecting it to the complex functions. For the set of curves f of xy is equal to c, the gradient vector del f is orthogonal to its tangent vector along the curve. So it's very easy to show that. That is essentially saying that f of xy is equal to constant, d of x is equal to 0, that is dou f by dou x into dx into dou f by dou y into dy is equal to 0, which can be written as a del dot f into vector dx, where vector dx is written as a dx into I cap plus dy into j cap, which is a tangent vector to the curve. From the above example, we can see that the curves u of x y is equal to x square plus y square and v of xy is equal to 2xy. We compute the gradient of these two, that is a normal to curve, which is del u is equal to 2x I cap minus 2y into j cap. V grad v is equal to 2y I cap plus 2x j cap. Clearly, we see that the del u dot del v is equal to 0. So this is essentially what we are trying to show by plotting them earlier. Now we can see that we can formally show that these two curves have their normals orthogonal to each other, which also means that their tangent vector is also orthogonal to each other. So we have a family of curves which are orthogonal to each other produced by the harmonic conjugate function or a complex analytic function. It's a time for an example. Show that the harmonic conjugate of function v of xy and u of xy such that the function f of x is equal to u plus iv is analytic in domain, then del dot u, then del u dot del v is equal to 0, which we have shown as an example. Now it is your job to show it formally using the Cauchy-Riemann condition, and these things are not usually very hard. And let me stop here and continue with the next lecture.